Section 21.12. The outer sphere mechanism. In the outer sphere mechanism, the electron transfers from one transition metal center to another directly. It does not go through any breaching ligand. In the outer sphere mechanism, the electron transfer may be viewed as electron tunneling between the two transition metal centers. There's no major disturbance of the covalent bonding or inner sphere coordination sphere in these two complexes. The rate constant of the electron transfer in the outer sphere mechanism can be expressed by this equation. Rate constant electron transfer is equal to nu sub n. Nu usually stands for frequency, in this case collisional frequency, nu sub n times kappa sub E times e to the power of negative delta G double dagger. This is Gibbs energy of activation over RT. This equation looks very similar to the Irene equation for the gas phase unimolecular reactions. Rate constant K is equal to kBT over H times e to the power of negative delta G double dagger over RT. So this part is equal to this part. So now let's look at this equation for the rate constant of the electron transfer in the outer sphere mechanism. This nu sub n is the nuclear frequency factor that accounts for the collisional frequency between these two reactants. Kappa sub E is the electronic factor that gives the probability of the electron transfer when the transition state is being formed. So over here we have the transition state already. We have the overlap between the orbitals from the two transition metals. And this kappa sub E has a value between 0 and 1, 0% to 100% after the transition state is formed. Now finally, delta G double dagger is the Gibbs free energy of activation. And this is simply the Gibbs energy of the transition state minus the Gibbs energy of the reactants. Marcus proposed that for an electron transfer reaction, delta G double dagger, the Gibbs energy of activation, is equal to 1/4 lambda times this squared, 1 plus delta G of reaction over lambda squared. So this is the equation proposed by Marcus. We will derive this equation at the end of this section. Lambda is the reorganization energy. This is the amount of energy required to move all the nuclei to the positions they adopt in the product. So I'm going to show you a picture for illustrating the physical meaning of lambda. Over here, this is lambda. Alright, so let's say we have the reactant here. This is the potential energy well of the reactant. This is the potential energy well of the product, right? Okay. So we're going to try to form the product from the reactant, right? So you can imagine this process. We can somehow provide enough energy to the reactant for this energy to go here. Alright, and it happens to be on the blue curve, the potential energy surface of the product. Okay, so you just imagine we excite this to here, and then it go from here to here, and then you form the product. Alright, okay, this is not the real process, how the reaction occurs, how the electron transfer occurs. I'm just showing you the meaning of lambda, okay? So you have two potential energy surfaces. Well, they may cross each other, and over here, okay, this is the equilibrium structure of the reactant. But if you go up, you may cross the potential energy curve of the product right here. Okay, this energy difference is the so-called reorganization energy. This is lambda. Okay, this is the reorganization lambda. So really, the true barrier is here. Okay, the true barrier is here. Okay, This is the true energy barrier. It will go up here and then go here, right? So you may imagine, well, we just need this amount of energy to go here on the potential energy curve of the reactant. And it happens that this curve crosses the potential energy curve of the product. So it can go back here. Well, of course it can go back to the reactant, but also there is a possibility this structure will go to the product side. So again, I'm using this to show you the meaning of lambda. Again, over here, lambda is the so-called reorganization energy. It's the amount of energy required to move all the nuclei to the position they adopt in the product. Now, for self-exchange reactions, such as this reaction, all right? So it's going to involve the transfer of one electron from this iron 2 to iron 3. The product is going to be iron 3 and iron 2. And it happens that all ligands are the same. So the products are the same as the reactants. In that case, delta G of the reaction is 0. So over here, you plug in 0 for self-exchange reactions. And once you put 0 here, this becomes 1 squared. It's 1. Delta G double dagger is just 1/4 of lambda. So again, let's get back to this picture. All right. So let's say this is self-exchange reaction. This Gibbs energy is equal to this Gibbs energy. They do cross. Okay, over here, they cross, and this is roughly 1/4 of lambda. So it's just you go through here and then go down. All right. You do not have to go all the way up here. You do not have to get this energy up by lambda. You just need to increase this by 1/4 of lambda. Why 1/4 of lambda? We can prove that later. Okay, so just get back to here for self-exchange reaction. You have 1/4 of lambda. But if this guy is negative, and that means, well, this reaction is very likely exothermic, and then you have a smaller Gibbs energy of activation. And what if this delta G is positive? And then, well, you just need to have a larger Gibbs energy of activation. So if you look at this equation, this Gibbs energy of activation does depend on the Gibbs energy of reaction. And actually, if this guy is really, really negative, let's say this guy is negative 3 lambda, okay? Let's say this guy is negative 3 lambda. Negative 3 lambda over lambda is negative 3. Negative 3 plus 1 is negative 2. Negative 2 squared is 4. Okay, and then your Gibbs energy of activation is 1/4 lambda times 4. Okay, so it's even higher than when delta G sub R is 0. So it's kind of strange. When delta G of when delta G of the reaction is 2 negative, actually you will have a larger Gibbs energy of activation. We'll talk about that later. So now let's look at this self-exchange reaction in this figure. So this is our iron 2, iron 3. All right, there's an electron here. Electron transfer is occurring. Okay, this is also considered electron tunneling from this center to that center. And now you have 3 plus, 2 plus here. Okay, now this is iron 2, this is iron 3. All ligands are the same. All right, so don't worry about the ligands. They're the same. And these two products actually are the same as these two reactants after the electron transfer. Okay. Now let's do a little bit of mathematics. It's possible for this Gibbs energy of activation to be 0 if your delta G sub R is negative lambda. You just plug in negative lambda here, and then you get negative 1 here. 1 plus negative 1 is 0. There's no barrier. Okay, there's no barrier. What if this delta G of R is less than lambda? Okay, if this is less than lambda, you get a negative number here, but still, this delta G double dagger is greater than 0. All right, it seems bizarre, but it can be explained by the following diagrams. Okay, now let's look at this. Actually, the first case with delta G double dagger equals 0. All right. So in this energy diagram, you have the product potential energy curve crosses the bottom of the reactant energy curve. So it's just going from here to here directly. There's no barrier to overcome, just going from here to here. Okay, in this case, this Gibbs energy of reaction is less than negative lambda. Okay, it's less than negative lambda. This one is less than negative lambda. Alright, and this number is less than negative 1. It's more negative than negative 1. So maybe it's negative 2, it can be negative 3. Okay, it's rare to be negative 3, but it can be negative 1.1, negative 1.2, and negative 1.3. Alright, so the Gibbs energy of reaction is very negative. But in that case, you still have a positive Gibbs energy of activation. How come? Okay, so in that case, this blue curve of the product does not cross this red curve of the reactant on its right hand side. It crosses on the left hand side. So it's kind of strange. But now in this case, it's clear. If you go from the reactant to the product, you need to overcome this barrier now. Okay, you need to overcome the barrier now on the left hand side of the equilibrium and then go down. Alright, so you go here and then go down. Alright, so this is really weird. This is really weird. Okay, so you have a very negative Gibbs energy of reaction. Okay, you go from here to here. Okay, it's highly exothermic, but in this case, you still have a positive barrier to overcome. You need to go from the bottom to here. And from here to here, you need thermal energy. You need to overcome the barrier. And then it goes down. Now, a bit more about this markers theory. So here's the diagram, and then we're going to do more derivations. So this is the reactant potential energy surface. This is the product potential energy surface. But in quantum mechanics, you may learn this later in more advanced quantum mechanics, usually graduate level. You will see supposedly this potential energy surface in one state and the other potential energy surface in another electronic state. They cannot cross each other. So actually, the true potential energy curve will be like this and this. Okay, they are not crossing each other. Alright, so this part comes from the reactant. This part comes from the product. But again, to avoid the crossing, so this is going to be a curve, this is going to be a curve. There's no crossing in the real quantum world. So really over here, this is your reactant potential energy well here. This is the equilibrium structure, and it just need to go through this barrier to get here, and this is the electronic state of the equilibrium structure of the product. So it's going to go here. What about this one? This potential energy surface may be considered as one of the excited electronic state. Okay, not this one. This is the ground electronic state. You go from the reactant side to the product side, and over here this is the excited electronic state. Alright, now again, for a self-exchange reaction, I'm going to assume both potential energy wells of the reactant and the product are both harmonic oscillators. And then we have a cross point in the middle. And then we can compute where this cross point is. We can compute this R. Okay, so if both are harmonic oscillators, R is different from A. This A is the equilibrium bond distance in the reactant. B is the equilibrium bond distance in the product. So we have this potential energy is equal to this potential energy because, alright, this transition state is right in the middle. And we're talking about self-exchange energy. Alright, so these two are equal, and then R is gotta be in the middle. It's 1/2 of A plus B. Alright, so that means the transition state structure is right in the middle between the reactant structure and the product structure. That's the physical meaning of this. And then again, we're going to use the harmonic oscillator approximation. We're going to calculate the barrier. So this is in the middle, and this is the equilibrium. So we have the transition state structure with this distance minus a. That's the displacement. And remember Hooke's law, half k times displacement squared. And then you get this equation. And this equation is equivalent to 1/4 of lambda. All right, because lambda is half k times b minus a squared. This is the reorganization energy. So if you change this equilibrium bond distance A to B, right, that's reorganization. How much energy do you need? You need half k b minus a squared, right? So that's why lambda is the reorganization energy. Okay, imagine you have a spring. The equilibrium bond distance is A. You stretch it to B. The displacement is B minus A. The potential energy is half k times displacement squared. And that's the reorganization energy. And it's called lambda here. So now let's look at this energy barrier. And if you look at this, well, it's just you have a 2 on the bottom, and this is 2 on the bottom squared. So you have 1/4 times lambda. Okay, that's this is actually the energy barrier, but approximately we can say that's free energy of activation by ignoring the difference between H and U, by ignoring the difference between G and H. Okay, because we're looking at the change. So the change of entropy cancels, the change of the value of PV cancels over here, roughly. All right, so what if you use this minus B? Actually, you get the same result. Okay, so this is R in the midpoint minus B. This guy minus B is also, A minus B over 2, but then you need to square it, so you get the same result. So that means the forward and backward energy barrier are both 1/4 of lambda. Lambda is 1/2 k times B minus A squared. 1 lambda is the reorganization energy. Now, what if the reaction is not a self-exchange energy? What if this Gibbs energy of reaction is non-zero? Well, we'll just solve this equation. Okay, we just need to solve this equation. So this equation tells you, well, this guy is equal to this minus this. That's it. This guy, this is Gibbs energy change of the reaction. Okay, is equal to this guy minus this guy. All right, and then we can solve this equation. I believe we can solve this equation. How do we solve this equation? This is a quadratic equation on the left-hand side, a quadratic function on the right-hand side. But fortunately, this r squared and this r squared will cancel. They have the same coefficients, 1/2 k. So you got this equation. So R is still the midpoint between A and B, but with a little correction here. This is just delta G of R over K times B minus A. All right. There's a physical meaning of this, actually. I think it's just this. When this Gibbs energy of reaction is negative, all right, the transition state looks more like the product. This R is going to be closer to B. When this delta G of R is positive, the transition state is closer to the... Wait, I think I got it wrong. So when this delta G of R is positive, this R is closer to B because this is positive. So R is closer to B. The transition state looks more like the product, the higher energy side. When delta G of R is negative, this part is negative, and then R is less than the midpoint. This R is closer to the reactant. The transition state looks more like the reactant. All right, that's one interpretation of this equation. But again, I mean, this over here, we're going to just use the expression of R and we're going to plug it in to get the Gibbs energy of activation. So really, it's actually the energy barrier, all right, using the Hooke's law. So we are making approximations. Well, we're saying the potential energy curve is a harmonic oscillator curve. So that's why you have this equation. This is Hooke's law. And we're looking at the displacement here. A is the equilibrium bond distance, and R is kind of the bond distance in the transition state. It's away from the equilibrium, so we have a displacement here. The displacement is R minus A. R is this, so we're just plugging in the expression of R here. So it's going to be this. More mathematical derivation. It's just algebra, but it's a little complex. Again, this is R. You may imagine this is the distance between two particles in the transition state, and it's non-equilibrium. So we have this non-equilibrium distance minus the equilibrium distance and square it times half k. That's the potential energy of the Hooke's equation. Okay. And then over here you have this guy minus A. You get this term. And over here I just copied that here. So this term, the second term, goes here. Half k is here. All right. And then I see this b minus a, so, and this is b minus a squared, so I'm going to take this b minus a squared out of this square bracket. So you have half k b minus a squared, and this becomes 1. All right, this becomes 1. In the second term, I do not have b minus a on top, so somehow I need to kind of create a b minus a on top, and then I have to square the bottom b minus a. So that's why you have b minus a squared. We're almost done. This is lambda, the reorganization energy. So if you go from the distance from the reactant, and that's the distance in the product, the displacement is b minus a, and then you use Hooke's law, you get half k times b minus a squared. This is the so-called reorganization energy. All right, so that's lambda. I put lambda here. Okay, this whole thing is lambda. I put it here. And I got 1/2 here, I got 1/2 here, and I have delta G of the reaction on top, and on the bottom I have K times B minus A squared. But remember, this guy is simply 2 lambda. This guy is simply 2 lambda. How is lambda defined? This is lambda, right? This is lambda, and therefore this is 2 lambda. Okay, so I have 2 lambda here. Now I have a 2 on the bottom here, I have another 2 on the bottom here, I can take them out. But this 1/2 is squared, this 1/2 is also squared, so I take a quarter. I put a quarter here, a quarter lambda times 1 plus delta G of reaction over lambda squared. And this is the famous Marcus equation that can be used to predict the Gibbs energy of activation if you know the reorganization energy and the Gibbs energy of reaction. I think Marcus won the Nobel Prize because of this equation and his theory on electron transfer.